Today's lecture is number 4. They have two topics. So first one is the tellurium and bismuth semiconducting materials, nanostructures. And then some second topic is the silver particles. This is the cover stories for the nano tellurium. Tellurium structures. The trigonal structures is has one strong chains. So the thermal property of the tellurium crystal have one-dimensional properties. And what is this is a problem? What is the structure in the nanoparticles? That is our first subject of studying the ICSAS. No. Oh, okay. Yeah. And this is from some textbook. How different the crystalline and the telluriums. This is another example of the telluriums, but this is compounds, cadmium and telluriums, bulk and nanostructures. The X-ray absorption spectrum is here, and exact Kaiki spectrum is here. Very simple structures function in nanocrystallines. Oh, the final panel is Fourier transform. First nearest peak is here, and second and third and further structure. We can observe the further structures. On the other hand, for nanocrystallines, only one nearest neighbor strong peak appears, as no other further contractions. Now, we call this type of materials hierarchical materials. The reason why the hierarchical is the first order structure is very strong covalent bonding in making the chains. And that chain are collected and gathered for the trigonal crystalline and make a three-dimensional crystalline. Analogously, the bismuth has a strong three-fold covalent bond, and it making the sheet, two-dimensional sheet, and three-dimensionally these sheets are stacked, and the very interesting show the interesting electric behaviors, the semi-metals. So our question is how change to the these interesting hierarchical structures to the nanomaterials. Of course, these materials has a amorphous state in the bulk, even in the bulk state, but the relation is very complex. Crystalline amorphous and bulk nanoparticles. That is our motivation. I show you our experimental setup. How make the nanoparticles? This is the island, because it's produced by the island depositions with sodium chloride. Sodium chloride is very chemically stable for the tellurium or bismuth. So on the substrate, the sodium chloride is mother species, mother materials, and inside the very small nanoparticles are produced. So we control the diameter of the nanoparticles by the deposition rate. The experiment performed by the photon factory in KK, Japanese synchrotron radiations. So we set the very close to the beam lines the liquid nitrogen pump tank, and this is a vacuum deposition. So first we deposit it to the here, and after that, we move to this holder on the beam lines. And X-ray is coming here. Sample is deposited on thin films. Why we use liquid nitrogen? These samples, tellurium and bismuth, are very unstable in the nanoparticles. So on the room temperatures, it easily become change to the crystalline. So I show you the 10 photograph of some certain thickness of the tellurium. We can find the nanoparticles, and this is a distribution of the diameters, and almost 50 nanometer, diameter is 50 nanometers of these structures. From the XRDs, this is the crystalline structures, and the small nanoparticles, there's no Bragg reflections. So this is a function of relation between our thickness controlled and real diameter estimated from the 10 photograph. So we call the 10 nanometer thickness about the 55 nanometers diameters, or this. Even in the 1 nanometer thickness, it has about 20 nanometer diameters. So this is a calibration line. Now here is the IXAS result, the Fourier transform of tellurium, tetragonal tellurium. It means the crystalline state, and 0.5 nanometers particles. The diameter of these particles is about here, about 20 nanometer diameters. So the low temperature IXAS shows the first nearest neighbor between the the covalent bond. And the second nearest neighbor peak is the interatomic interchange relations. And the third one is another intrachange here. And fourth, and so on. For the nanoparticles, the first nearest neighbor is a peer, naturally, and the second nearest neighbor is very small, and third is no more appears for the high temperatures. The interesting result is here. After the curve fitting, we obtain the interatomic distance of the interchange first nearest neighbors. In the bulk states, the distance is around 2.83. This is a typical length of the tellurium compounds. So the thickness in degrees, or diameter also degrees. The interchange distance also degrees. So it means the breakup of the intrachain contribution relations and the bond length, bond strength is increasing. So about 10 nanometer thickness, it steadily goes down. Another characteristic structure is coordination number. This is the intrachain coordination number, second nearest neighbor coordination number. So first nearest neighbor is naturally 2, n equal 2, but interchange has 1, 2, 3, 4 around here. So this coordination number degrees from the number 4 to 3 or 2. This means the chain structure is conserved, but this three-dimensional stack are broken down. Now we consider the bond strength from the Ixas result. This KB is the empirical bond strength calculated by the just bond interatomic distance. So as the thickness decreases or diameter decreasing, bond strength increasing here. That is the inverse relation to the interatomic distance. Another one is calculated for the Einstein temperatures. We already discussed yesterday. The bipolar factor has a relation to the Einstein frequency or Einstein temperature. So this bond length from the Einstein models increasing for the nanomaterials, nanoparticles. And we plot the intra-atomic first nearby distance for 2.83 to the 2.78 versus to the interatomic coordination number. That is about 4 to 2. We found a very clear relations, linear relations. This result means that as the breakdown to the chain relations make the interatomic distance intra-chains the strongest. And the analysis of the bipolar factors. Oh no, this is just yeah. We already discussed this iron models, so I skip this one. So this is tellurium nanoparticles for intra-change. So nanoparticles show the red line, and crystalline is blue lines. The temperature as a function of temperature. It's best good fitting to the Einstein models because the covalent bond is quite harmonic. So the Einstein model is good approximations. So becoming the nanoparticles, the inclination of this curve is decreasing. It means the bond make the strengthened. Another one is the interchange. The interchange is a chain relation between the change from crystallines and nanoparticles. This inclination increasing is meaning to the bond weakened. So we can compare the Einstein temperatures or Einstein bond strength like that. So the strength of the interchange weaken and interchange go to the nanoparticles. So our roughly model is the crystal structure is here to the changing the Young models. Complicated, mixed the change. Unfortunately, we didn't determine direct information from this type of structures. This is just our explanation, expectations. The daughter of my colleagues, Professor Ikemoto, was very small, so she praised this type of yarns in his rooms. So he discovers the model of the nanoparticle models. But it is interesting to in the surface state, in the crystalline state, there is a many dangling bond. But in this case, we hope to the no dangling bond in the nanoparticles. So the different electric properties are expected. The second topic is the bismuth nanoparticles. As I show you, the two-dimensional sheet are stacked to as three-dimensionally, and this is the result of from the XRDs, crystalline state and nanoparticles.